Testing, testing. Testing, testing.
Hello, everybody. Third microphone in. I think we've got it down finally. So, if you didn't hear before, welcome everybody to the PCB Design and Layout webinar hosted by CUAUV. Awesome, so let's get started. Okay, so during today's webinar, I'm going to be talking a little bit about custom board design and kind of the steps to first coming up with the schematic and then ultimately making a printed circuit board and getting that sent out, manufactured, and tested. And then just some general tips that you should keep in mind when doing your custom board design. So I guess the first question is why actually making custom boards instead of getting things purely off the shelf. As you might have heard in the previous electrical webinar, comparing the two, you get some really good reliability. There's a lot of great option if you're going off the shelf. When you make it custom, you really have the opportunity to adjust the form factor. So say you want to minimize the size of your vehicle, and you don't want to have a bunch of off-the-shelf components that are really large, and this really allows you to kind of customize your design. It gives you a lot of great experience working with the components and a better feel for how the devices actually work when you're writing the code for it and just kind of playing around with parts. And then it gives you the option to really tune the parameters of your design. So, for example, and I'll talk a little bit more about it later, is say, for example, you're looking at a battery pack and the chip you're looking at has a certain cutoff where it just stops communicating or detecting pack voltage when it drops below a certain value. By being able to tune that threshold, then you can make it a little bit more application specific. You can do recoveries. You can still maintain whether or not you've lost connection because like connection's actually lost or if it's just a low voltage state. So there's a lot of cool things you can do. Cool. And then the next question, I guess, is if you've decided to do a custom design, deciding how custom you actually want to make it. So I kind of break it down into 3 different levels where you have the first one that is purely off the shelf. The second where you would be making your own design but kind of integrating a lot of off-the-shelf components. So for example, on our team, we implement our microcontrollers as like the individual microcontroller chips versus a lot of teams I know use Arduinos to power their like motor controllers and stuff. And our microcontroller is basically that same IC that you see on like the Arduino board, but we just kind of, by having it as an independent component, we can get rid of a lot of the complexities that we don't need and then add in just the functionality that we do. So that kind of goes into the lower level implementation where you're basically, you're kind of taking already made designs and kind of implementing it as your own custom design. So for example, you're making your own H bridges instead of buying dedicated ICs for that. My example for battery management is, for example, they have dedicated battery management circuits, or fuel gauge ICs as they may be called, which kind of do the voltage, current, temperature monitoring for you, and you read the data coming out of it. Whereas last year we were trying to implement it using diff amps and buffers, and kind of implementing the 3 sections on our own. Less power efficient, but it was kind of cool. It allowed us to kind of tune those thresholds a little better. So I'm going to go a little bit into definitions. Actually, really quickly, I forgot to mention, if you guys have any questions during this webinar, my email is msh276@cornell.edu. Send me any questions related to the webinar or anything, and I'll try to get back to you at the end of this, at the end of my presentation. Okay, so into the definitions, things that you'll probably see when you are designing is, first off, you've got your printed circuit board, which is the physical board that has different pads and traces. It basically is the platform for your design. Next, just kind of as a more broad term, what we're actually designing are embedded systems, which are where we use some kind of microcontroller, some kind of software in order to implement something in hardware. So that's anything from driving motors to interacting with kind of like temperatures, any kind of sensors, and then going a little bit into just computer-aided design, which is basically what this whole process is we're going to simulate everything as a schematic, as a layout, possibly run some simulations, just to kind of make sure that our designs work. A little bit more into that is we've got schematics, which will basically be a representation of functionally what your board should be doing, with part numbers included, connections between boards. Components, and then ultimately your layout, which will be kind of like the PCB design, where you actually get to, this is exactly what's going to be printed, exactly what you'll be using in your vehicle. Okay, so now before starting any project, you want to make sure that you have kind of, you break down the task into what you need your board to do. And then setting goals and kind of priorities for the task. So for example, if you're making like a custom thruster controller, what does that mean? Well, you're going to need something that'll drive the motors, such as like an H bridge, and that's something you'll see just kind of researching some different like implementations. And then once you know that you need that, and you've got like your microcontroller that kind of lets you talk between your computer and kind of controlling the motors, then just kind of populating the board around that. So for example, okay, so now if we're looking at this like thruster controller board, you can kind of see we have our H bridges in this region, and we've got our nice outputs to our motors. In order to control H bridges, we have some drivers, we have a bunch of gate enable lines, and then for example, so we don't need to pass too many voltage rails to this board, we kind of made the design choice to take in 24 volts to control our motors, and then level shift that down to 5 volts for our microcontroller. So really just kind of defining what you want your board to do, what components you think are going to be on there, and then just kind of building your design around that. Okay, so when it comes to kind of researching, really a great place to look is really just online. A lot of people will post kind of little projects that they're working on. A lot of companies will have kind of application notes that if you're trying to make a design, they kind of give you like a how-to, like how to approach it, some of the chips that they'll actually use, and it has really good documentation. Um, so yeah, one big area to look into is like hobbyists who will post a lot of like do-it-yourself, thruster controllers. Last year when we were integrating our LCD into our vehicle, the application like circuit that we found was actually very closely related to something we saw online. Just looked up the LCD part number and it popped up and it was really helpful. It worked, and yeah. So really using the internet or yeah, as a resource, and then just kind of looking again, looking at what you want the board to do. So functionality, feasibility. So maybe you want to do something like super crazy, just making sure that like it's actually doable. Is always good. And then ultimately trade-offs. So you're looking at maybe area versus cost versus, maybe having a lot of like cool features implemented on your board. Um, okay, so again, this is kind of looking at, or as kind of an extension of a little bit more background still. Deciding now that I know what I want to do. So now I want to build a custom motor controller. Deciding now how I'm going to do that. Um, so that requires a lot of communication between you, the mechanical and software kind of constraints of your vehicle. So say you're driving a motor, you need to know what type of motor it is. The data sheets are a little bit lacking. Usually they're kind of short, but if you can at least pull things like power specs, maybe update rate that you need to send your signal at for proper operation, whether or not you need some kind of encoder to know positioning of your motor, depending on the type of motor you're getting. And then kind of going back to power specs, you're looking at is this a 24-volt motor? Is this a 12-volt motor? What happens if I drive it a little bit higher? And then when I say communication protocol, that is mainly knowing what your system supports. So, for example, we do use RS-232 serial for a lot of our board communication, and a really great or one of the big reasons is because a lot of the sensors we use support that, and it's good to have everybody kind of sitting on the same protocol. That way you can have a single board that you're debugging instead of trying to communicate to three different or instead of having to make so many different hardware implementations and then communicating that way. Okay, so now I'm going to move into kind of the design portion, where it's now that we know what we want to make, now we know how we kind of implementation-wise want to make the board, just the tools that we actually use. So in the design software, so actually in this section I'm going to be talking mostly about what we do, and there are a lot of other tools out there for you when it comes to like printing boards. There's a lot of different manufacturers. So yep, if you guys have any questions, or if maybe your team is using a different company, it would be great if you could reply to this video, and we can kind of get a conversation started. So in the design software, so this goes back to the computer auto assisted, oh my goodness, I'm sorry, design software. We are looking for, so we use a program called Jita, and it's good because it's free, open source. It's, at least for us, we find it very sustainable. You know, because we have such a large team and we've been around so long, it's nice to be able to open up a board that existed, you know, a couple years back and still be able to look at designs, look at why are we implementing this way instead of how they implemented it back then, and really just for continuity's sake. In addition, Eagle CAD, which we got a really great sponsorship from, and we've been using, and Eagle is actually really great. The thing is that it's quite expensive. They do have a free version, but you can only do up to, I think, 2-layer boards. So if it seems right for your team, it's actually a really great tool to use as well. And then you can also, the nice thing about Eagle too is you get features where you can, for example, the schematic and layout, say you make edits in one, it updates in the other. And you can also export it to test in other programs, like I believe LT Spice will do that for you. And then you can test that your designs actually work. Cool. And then, so yeah, just kind of looking at cost, number of layers. The nice thing, Jita lets you do up to 8, I believe. And then looking at built-in libraries. So, you know, the nice thing about having something open source is that you can look around. There's a lot of people who actually make footprints and symbols on their own, but it's not as, or it's a little bit more customizable. So what's nice about us is because our team's been around doing this for a while, we actually have built libraries of components that we've used, and yeah, so basically any member can access, you know, say we used this AND gate a while ago, well now we have like a chip that we think works well and other people can use as well. And if you're using something like Eagle or anything like that, typically they'll have pretty extensive built-in libraries, which will have a specific part number, a specific footprint, and like specs associated with it. So that's cool. So the first step in a design would be to have some kind of schematic, which again is the kind of, you're basically using a bunch of symbols. You can see how all of the boards will interact with each other. Okay, so actually now I'm going to go a little bit off and show you some actually examples of schematics that we have. And okay. Okay. So I'll head back to that slide actually in a little bit. So you know, when you're making a design, or a schematic, you want to have a few things in mind. First off, because this is functionally how your board works, you want to make sure that it's easy to look at. You know, if you have a, if point A is connected to B, well, you can either route them like in this crazy loop around the board, or just making it really easy for somebody else to access. It's good for longevity purposes. So say the person who's designing the board the year later wants to kind of see what you've done, then again, making it really easy to use. And then when I say labeled fully, it's making sure that, sorry, again, it's just easy to use. So here's the example. I'll kind of compare and contrast. So in a design like this, So what we're looking at right now is a battery management board. And this is actually a board design that we had from a couple years ago, and it worked very well. This implementation used the fuel gauge IC, and in order to monitor the voltage, current, temperature. As you can see here, we've got like our IC, we've got our microcontroller, and some serial level shifter. Um, right? And the design works very well, and is a good reference to use. Now let's compare that to, so it's actually the same board done last year. Implementation was a little different. Um, as you can see, just like a big contrast is now, for example, as I've said, we've now uh, done what we call net names, which basically identify what each like wire connection is called. So now you can say that, oh, I am sorry, something crazy is happening. Um, so you have, say, cell 1, you know that is connected to cell 1 on the input connector, which, oh dear, yeah, over here. And it's a really great way to kind of identify that they are connected to each other without physically drawing a wire shooting across the board. Another like tool that I find nice are having inner schematics, which basically means I can have this symbol on an external layer, and then within it are like components that I can use, and it makes the design a lot easier to kind of handle. Um, cool. Yeah, if you guys have any questions about like schematics, really, as far as how to use them, it's very specific to the program you're using. So really that just involves a lot of playing with, learning how to make your own symbols, make your own footprints. Um, cool. Okay. So now let me go back actually to that slide that I was talking about earlier. Is about kind of just choosing the parts that are right for you. So already you've done your research. Say you want to find, for example, like a DC-DC or like an LDO, and um, you don't know where to start. Kind of, hey, I want it to step down 24 volts to 5 volts, but I don't know um, kind of where to look for the components, what's good. Um, Kind of, there's a few companies that we like to kind of go to. For example, we've got TI, Analog Devices, Linear Technology. They're really good because they do have a really nice sample system. So it allows you to kind of play with components that you want to potentially use. And yeah, and the nice thing is a lot of companies too will have deals with universities that if you're a student, you can get maybe like 25% off their components. So we use at Mega microcontrollers, and Atmel has a nice like university program. Cool, and then just kind of starting. I would start at a company like that, do a parametric search, which allows you to put in, here's my voltage range, here's my expected current draw, here's the footprint I want, and I'll talk more about that later. And then kind of deciding from there what you want to use. And then when I say added complexity to other systems, it's okay, when we're looking at added complexity, it's now that I have a component, like say an ADC, am I choosing an ADC that needs an external reference voltage in order to set the kind of range of values you can read? Use. and just kind of looking at the parts that way. It's really a kind of trade-off system between kind of cost and functionality. What do you actually need your board to be able to do? Okay then. Um, okay, and now we go into the layout portion. And just to reiterate, the layout is actually the physical board design. Um, so when I say it should make sense from start to finish, that just means that really when you're using your board, you don't want to have to, or it should be fairly systematic. Layout is actually the kind of nice, kind of aesthetically pleasing portion of the project, and making sure that, yeah, if I've got like my ADC and my reference voltage chip, like they should probably be close together and not, all the way across the board. Um, yeah, and kind of just grouping things that way and making sure that, like, say somebody who's never looked at your board before can kind of look at it and say, hey, this kind of makes sense. Here's the input power. Now we're moving into some voltage regulators. Now we're moving into like specialized ICs and stuff like that. So yeah, I'm gonna now show, I guess, a couple of like layouts that we actually have on the team. Okay, so there are a couple of things to kind of keep in mind when you are designing your boards. Here's actually our serial board from last year, which basically takes in our USB input. It takes it to a hub, which then splits it into several USBs. It goes into a 4-channel FTDI chip, and then we do some level shifting, and it turns into serial. So I know we had a question about that last time. And so as you can see in the layout, what's nice is because it's so modular, you can kind of tell, like, here is a channel, here's another identical one. And it makes debugging really easy. So whether or not you actually made this board, you can kind of tell, like, I think these are going to work in similar ways. Hey, I've got one channel working, and like certain debug points, well, they're going to be the same on the second channel. And I think just kind of designing your layouts like that is kind of nice as well. As well as in terms of debug, we've got like our nice indicator LEDs, which will tell us if we're actually communicating. And that way, when the hull is sealed, we can do some debugging without physically being able to access the board and probe voltages, which is cool. And then looking at kind of like how do we decide on maybe the connectors that we're using. So here's actually slightly different things we did. Yeah, actually these are both blind mate, which basically means it's a board-to-board connection. You can slide in your board and they'll basically interface without you having to like plug things in. As long as they're aligned, it'll make a good connection. So here's kind of the difference. We've got this type of connector from last year, which was kind of bulky. We made a shift into kind of just using like a PCIe slot connector. So this is actually the same board, or same functionality, but now this is the layout we've done this year, and we've got some differences. We still have our hub, we still have our 4-channel FTDI chips, but now we've also expanded to, as you can see, we don't need as many of these. We've got slightly larger shifters, and now we can actually have USB capability on this board as well. So as you can maybe tell, is the form factor is also very different. And this is because we build vehicles so often, this kind of we can do big changes like this. If you're designing for a multiple year process, you probably don't want to make it too specific or too constrictive, as in terms of like mechanical design or fitting into kind of the mechanical design of the vehicle. Um, so yeah, again, we've got our nice indicators. We've got these really good test points so that when we're on the bench, we can actually test this board. The problem with a connector like this is that there's really nothing that you can probe, like with an oscilloscope while you're testing. So having like dedicated test points is a really good idea. Okay, so when we're looking at choosing components, and I can go back to the layout and show you a little bit what I mean. So we're looking at certain components are actually meant to be soldered by hand. Other ones are definitely not, and you would end up using like a reflow oven, or for example, some companies, and it's kind of an option you can get, they'll populate the board for you, which is nice as well. But so a couple of things you'll probably notice when you're purchasing components, you have your chip resistors will be labeled in this manner, and this is basically it's looking at it in mils, which is thousandths of an inch. So this would be like 60 mils by 30 mils. And then, so that's a fairly small component. But I would say that's about the smallest you can get soldering by hand. We use 0805s, which are slightly better. We lose a lot less of those when we're trying to solder, so that's always great. And then through-hole components, which you're probably more familiar with. Say you're doing like breadboarding, you probably would have used through-hole like resistors, capacitors, and these are really easy to get a good solder connection. The problem is that they're really big, they tend to be more expensive, and so when we use these, they're for either things that we need to make sure are soldered really well, and the other options are really difficult to solder. Or if, say, we have a larger value capacitor, and instead of ceramic, they want us to do aluminum, well then typically we would be using through-hole like components in our design. Yep, so actually let me take a step back at the layout and I'll show you a little bit more. So here are all of these like chip like resistors and capacitors I was talking about. They're very small. You may not be able to tell from like looking at this right now, but yeah. Here's that. We actually have our components. What's nice about this particular package, oh, so something you'll notice about a lot of components is that they'll come in several different packages. So this particular one is gull-wing, which means that the pins will extend out and you can actually solder them, solder the leads from the side, as opposed to say something like a QFN, which and I apologize, I can't recall what it stands for off the top of my head, but basically it has all of the pins situated underneath the component. So really the only way to solder something like that is to basically heat up the full, like the pads and the chip, getting everything at once. So that would require like an oven. The problem, because we do everything by hand, those aren't things that we can use. So that plays another factor when we're like choosing components, is whether or not we can actually solder it, and if not, unfortunately we have to find something else. So okay, I'm just going to discuss a little bit tips for an effective layout. I'll show you the slide after that has the specific tips written down, and if you guys have any more questions on layout design, shoot me an email. I'll try to answer it. So kind of when I'm making a layout, the first thing I want to do is kind of group like components together. So for example, I'm making this channel. Let's find something that works nicely, because once I know, or once I have one that works, the next one should be easier. And just really like pre-planning. Um, uh, okay. The next thing is when you're doing high-speed traces. So this board, so probably the fastest signal that we need to worry about in our vehicle is USB. So as you notice, like these are actually our USB traces. They're very isolated because they're high speed. They're not hitting right angles, because that would increase like the number of reflections, and kind of the integrity of our signal would go down. And yeah. And as far as, how do we actually find out things about like USB traces and how to actually lay them out properly, we just did a lot of research online, and we found these great documents that said basically just kind of like tips on how to actually lay out USB/high-speed signals. And then just kind of implementing it, we find it works really well, and this is kind of how we've done it ever since. Another thing to keep in mind are things like decoupling capacitors. You want it to be near the component that is actually decoupling, and those are for stability purposes. So, see if I can find a good example. Yeah. So things like this. It is on the back of the board, but as you can see, it's really close to the pin it's trying to decouple. For example, things like your crystal, because it's used for kind of precise timing logic, you want to make sure that these traces leading up to it are basically the same length. Little tricks like that, and really, if you're ever wondering like how we get to this point, how we decide on, or how we figure out like the best way to lay out, is really just a lot of online research, and seeing how either companies recommend us to lay things out, or even just maybe people have tried it on like forums, and they found like a certain technique works better than others. So yeah, I've got a list of tips for an effective layout, and this is by no means everything. And really a lot of it you'll get from just trying things out. Oh, apologies. A little bit, just a couple more things to keep in mind. You remember earlier I mentioned number of layers. So in the past, we've actually done combinations of 2 and 4 layer boards. 4 layer boards, if it's more complex, we find, say the serial board, which I just showed you, we actually have this giant, we use the entire second layer as a ground plane, and this works really well for shielding. So when we're running our USB traces, it's not passing over different potential like crosses. So say had I put the power plane right beneath it, and it changed from 5 volts to 3.3, then back to 5, you would actually see some noise fluctuations on your like signal. So yeah, that's something to keep in mind. 2-layer boards, something you really need to watch out for is actually just pre-planning those ground planes and those power planes, and making sure that you've dedicated, or that instead of running like a itty-bitty signal trace that weaves back and forth throughout the board, you can actually just make like a central branch and make it kind of like a tree structure, instead of so that the return path from like a specific component is as short as possible. Because we don't worry too much about it on the team, but things such as parasitic resistances and capacitances, you'll notice the longer your trace gets. So something to keep in mind. And then a big thing is the design rule checker, which that is specific to the company you're getting printed from, but basically it's a list of rules that tell you what the manufacturer can actually print for you. So as far as like the width of or the spacing between traces, companies will typically say 8 to 10 mils, and again, that's thousandths of an inch, and that just means that's the closest your traces can get. Any closer, and they don't necessarily guarantee that they won't short together. So it's something to keep in mind. Whichever company you decide on, just kind of talking to them, finding out what those specs are, and making sure that you're designing around it. Okay. Now we're entering into board manufacturing. We don't manufacture anything in-house. We actually get them sent out. We use NextLogic, who's really great. They actually get it back to us in 2 weeks, and they've been a sponsor of our team for a while now. And there are a lot of great, like pretty cheap companies out there where you can get your boards printed. And then there's always the option of whether or not you want them to populate stuff for you, if you're going to do it, and really just, yeah, deciding how much you want to spend, and if you want experience soldering and such. The Gerber files are actually the files that you'll send to the company, which is basically a breakdown of what each layer is. It'll also give you specs such as drill size for your vias and your pad or your through-hole components, and that's all included in those Gerber files. So most of these design softwares you'll be using should be able to export these directly, and yeah. Cool. And board testing and debugging. I'm sure if you've worked with a circuit board before, you definitely know how to do this. Because something that we find on our team especially is that we need to spend the most time testing and debugging. I'll go a little bit into like the calendar that we actually kind of aim for. We spend about half the year testing and debugging because we know that most likely our first design won't work, but the earlier we get that sent out, the easier it is for us to kind of make changes, send out another revision, hopefully get something that is ready to go in the vehicle and works really reliably. So as far as testing goes, if you're going to be doing soldering yourself, you're populating the board. When I say in order, it means we're going to do power regulations because we don't want to fry any of our chips. And then as far as soldering goes, you kind of want to work inside out. So typically you'll have your big IC kind of at the center of things, and then your capacitors around it. So you want to start at your IC, because if not, then it's very hard to access. And then having, and then for the sake of debugging, having well-labeled test points and LEDs really allows you to, the LEDs are great because by inspection you can see, hey, the board's not communicating, hey, this channel has turned off, it's not outputting power anymore. And that's really good to be able to do without popping the hull. At least for us, removing the hull kind of takes a while, so being able to do just kind of visual indication is really great for us. Another thing is if you have certain debugging registers in your file that you send to your software team, they can always pull and say like, hey, here's the current draw coming from the battery packs. I think we should shut it off. Things like that. And test points are great for testing on the bench. Usually, yeah, as long as they're labeled pretty well, they're easily accessible, then you should be able to test it in the vehicle. Maybe the LED wasn't soldered well, and now we're just double checking whether or not our valves are actually firing, or or if some kind of connection got broken, well, now we can see like if the signal's making it through without accessing like the connector output, which is really great. Okay. I actually apologize. In making this presentation, I noticed now I didn't go into coding as well, or as much. Because this is an embedded systems design, something to keep in mind is that you're really balancing like the software portion with the hardware portion. Because you use the code on the microcontrollers, to kind of implement, say, we've got this side of the motor firing now, or we're reading in values from an ADC. So if you guys have any questions about that, we can either add it to like a future webinar, or I'd be happy to take questions at the end of this presentation, just about like the hardware embedded C coding that we do on the team. Yeah, so back to the slides. So something to keep in mind is kind of scheduling. So I've kind of put down the steps to kind of completing a full design. There's a lot of things going on. We go through this design cycle every year. Start with research, then deciding what you want the board to do, prioritizing which tasks you want to accomplish, and then from there choosing or just kind of building the schematic around that. So including voltage regulators and any kind of monitoring that you need. Choosing components that meet all of your power specs, and they're in a good solderable package. Maybe you'll be running simulations, which we do for a handful of our projects. We actually look at how they'll behave, under different loads. We were testing out like a custom DC-DC circuitry, and we were running simulations to make sure that like the filter network and everything was pretty solid before we sent out the board. We have then we go into layout, and just keeping in mind, layout actually does take a really long time, because when we're making boards, they don't have 5 to 20 connections. No, they have hundreds. So just keeping in mind that you got to do a nice, got to get everything organized before you make connections, and then sometimes you'll make connections and then realize, oh, I could have done this more efficiently, and you end up redoing your board. So just really budgeting time for that. After that, boards get sent out, come back. We do soldering, testing, and debugging. We write the code to test, is the heartbeat LED, which kind of shows us correct operation of our board, like it's not getting stalled or in a weird interrupt state, or I'm sorry, timeout state. Giving ourselves time to test our code. And then at the end, I say iteration, because even for us, boards don't always work on the first try, and making sure that you've given yourself enough time to kind of tweak things and get it to a point that you're comfortable putting that in the vehicle. So I just gave you some numbers, actually. So we do most of our board design in the fall semester, and that takes the entire semester. So that's about 4 months. That includes schematic and layout for the first revision. Sorry. And then we get into soldering and implementation. We say a month because we have kind of an ambitious in-water deadline. So this is as soon as we get back in the spring. We spend about a month, writing, testing code, and then the vehicle gets in the water, because we try to give our software team about 5 months to test. Typically what we'll find for the first couple weeks is that we're breaking in the new electrical system, and sometimes things will break. When you're putting a board under the actual load that you'll be driving your vehicle at, sometimes you'll notice that it'll catch poor solder connections. So say, this FET on my motor controller wasn't soldered as properly as it should have been, wasn't making full contact and overheated. That's something you'll notice in the first couple weeks of testing. My recommendation for that is really to when you're on the bench, to go and test components, like with the physical thruster. You can't simulate the same load of it being underwater, but you can at least kind of get a sense for testing the actual component, which is a good idea. And then as far as board printing, 2 to 4 weeks, depending on the company. Ordering parts, We use DigiKey. Um, but yeah, making sure that you give yourself about a week for that. Same as sample requests, and samples again are like TI, linear technology, um, because those do take several days to come in, and it could kind of um, so for example, when you're waiting for your board to get sent out, maybe sample your parts, order parts. Um, Actually, something I didn't mention earlier was before we send out boards, something we like to try to catch, hopefully are footprint. I'm sorry, footprint mismatches, which basically means that once we have our layout done, we'll print out what we say a one-to-one, so it's a one-to-one scale of our board. Um, we will order the parts and we will check that the part that we ordered actually matches the footprint that we think or that we've included on our board. Um, it's kind of a low-tech way of doing things, but it's good because we actually do catch several times that maybe we thought we were using one component, but we're using the other, or like, um, yeah, and just making sure that things match. And this is like a nice visual way of doing it. Of course, you can always just measure like the width between pins and specs that way because the data sheets for chips, at least footprint-wise, are pretty good. Um, cool. And then another thing that really helps us keep our schedule is having multiple stages of design reviews. So the way our electrical team is kind of structured is this really nice tree structure. So we have, or like a nice hierarchy. So we have like electrical team lead, and we have our sub team leaders, um, and so each person is in charge of maybe 3 to 4 people, and this way um, we can have a small like preliminary design review where the person working on the board will meet with their sub team leader. They'll try to catch any obvious mistakes. Maybe we made an error in the schematic. Maybe maybe one of the footprints is very clearly wrong, and then we'll take it to a full electrical team review. And we try to plan design reviews with about a 2 week for somebody to 2 to 4 weeks to do the design, and then once they have their first design done, then we'll typically have design reviews set about a week apart. That way we can just double check on the progress, make sure that as people are making changes, they don't, they don't take a step in the wrong direction. And you're really just having like regular meetings with sub team leader, and if your team isn't broken down that way, um, even just having another pair of eyes to look at your board, because at least I find when I'm looking at my board for days at a time, really I'll miss things that somebody else could look at for a second and just automatically see is an issue. So yep, just having like regular checks with someone else. Um, okay, and then finally is really making sure everything is documented really well. Um, if the old schematics and layouts are accessible, you could always go back and look at that. But I mean, you don't really want to spend time figuring out how the board works. Documentation is great because it'll tell you what worked about the design, what didn't work, and improvements, and potentially reasons why you made a slightly different design choice and the board went in a different direction. So we actually have several different types of documentation. We have our technical design docs, which are basically just kind of the implementation of the board. So, here's the topology we're using. Here is how it works. Here are why I'm including all of these different ICs. You break it down into kind of the same way. If you notice in the schematic, you've got like a power section, you've got your microcontroller section, breaking it down that way. Um, and then just really explaining the design. And then we do like a small reflection about like, here's why this design works really well, here's why it doesn't work, and here are things we can do better. And then we have a user manual, which is straight up, here's the order you'll populate it in, here is how you would use the code, because sometimes people will make test codes. So if they just want to test, that the heartbeat LED is working and they don't care about functionality, maybe they'll flash that on. And then also just, possible failure modes. So we run into a problem over the summer where a lot of people who worked on the board during the year won't be around. And this user manual allows us to say, like, hey, these test points are here, this is what they do, if I'm seeing my heartbeat blinking really rapidly, maybe I've timed out, and here are the steps to kind of fix it. Because the person writing the documentation should be the most knowledgeable person on the subject. And just really, just for longevity purposes, documentation is your best friend. And this is my last slide, just recapping everything, generally tips for custom board design. So first thing you want to do is research, and then going from there. Aggressive scheduling, I realize the schedule that we actually stick to is quite accelerated, and I'm not saying it's the appropriate one for every team, but just making sure that whatever schedule you stick to, and making sure that everybody's kind of pulling their weight, and if they can't, then just kind of figuring out, like, how will we achieve our, if we need this design to work, how will we make sure that it gets done? And then again, saving a lot of time for integration and testing, making sure that the board is working. You don't you don't run into a strange case in your code where you like shoot through your H bridges, and that's never good. And then just documenting everything really well. So that is it for my presentation. Again, if you guys have any questions about like the embedded C coding, I apologize for not going into that. I'd be more than happy to answer any questions about it, or again, like maybe host a short webinar about it. Again, if you have any questions, my email is msh276. And I'll stay on the line for a little bit just to see if any questions come in. As of now, I don't think I've received any. But yeah, thanks for tuning in. Okay. Yep, on that note, I think I'm going to sign off. Again, feel free to shoot me an email whenever. And yes, thanks again for coming.